My name is Sophia Flucker. I'm from Operational Intelligence, and I'm delighted to chair this Isotope webinar on data center liquid cooling. So as IT equipment densities continue to increase, it's going to be increasingly difficult to support cooling using air. So liquid cooling solutions are going to become more mainstream. Today, we're going to be hearing from our esteemed speakers who will share their insights. Following these presentations, we'll have a Q&A session. So please add your questions to the Q&A box. You should be able to find that at the bottom of your screen in Zoom. So on our panel, we've got Malcolm Howell. He's a mechanical building services engineer who joined Cundall in 1994 and is now a partner. He leads the Global Critical Systems team, which specializes in the design of data centers and other mission critical facilities. Malcolm has focused on the design of data centers and has a particular interest in energy efficient cooling solutions for data center applications. In this context, he's been involved into research into the effectiveness of free cooling strategies and the impact of cooling system failure, as well as working on award-winning projects. Cundall have been commissioned by Isotope to undertake an independent study on liquid cooling, requesting a detailed analysis, as well as the impact on data center operating costs. So we'll be hearing from Malcolm on the findings of their analysis, including the environmental benefits it can deliver. We also had Gerard Thibault, the CTO at Cow Data, who draws on more than 40 years of experience within the electrical engineering industry, and more specifically, 20 years as a technical thought leader within the international data center sector. Gerard joined Cow Data after an 11-year assignment at Digital Realty Trust, where as Vice President of Design for the EMEA region, he had responsibility for the design and implementation of over 150 megawatts of data center space across 24 sites globally, including 15 new build European projects. Gerard will share with us KO's experience of liquid cooling and how they see this journey continuing. We also have David Craig, CEO of Isotope, who's had a varied career with experience holding global procurement roles at Unisys and IBM, leading the commercial integration of Prudential Assurance and Scottish Amicable, as well as helping grow various startups. So to get us started, David will share some details of their development of liquid cooling products. You might see on the panel a couple of others in the background who are kind of supporting us from a technical perspective this afternoon. So I'll hand over to David to get us started.
Sophia, thank you very much, and to everybody who's joined us today, our gratitude for your time. I'm not going to spend long talking, but just really to build on and set the scene. We commissioned Cundall to do this report, and we also work with Gerard and the guys at KO. We're really proud of the work that's done there, and we're really grateful for the quality of it that Cundall have delivered. The timing of liquid cooling and the different approaches to it matter, and I'm not going to show technology shots. Malcolm's going to talk about the technology differences. But our whole approach as Isotope was not to make something that was complex, but instead to approach liquid cooling from a point of view that said, how do you deal with everything? How do you deal with the whole stack? How do you deal with servers, GPUs, storage, switches, everything? And how do you do it in any scale? How do you do it from hyperscale to the first hop edge? And we've really been on a mission to make sure we could do that we could make something which was both familiar, because it fits in standard racks, it fits and retrofits into technology that people have already, and you can see a real roadmap through to the future. And we've worked hard to make a roadmap that not only deals with the problems of today, but deals with the next several generations and beyond of where technology goes. And we've got a solution that we think uniquely deals with all of those challenges and allows us greater legs than any other approaches that exist there. We focused on simplicity, and we focused, as I said, on complete scalability through our business model. I hope you enjoy today, and it provides useful background, and we'll always be happy to follow up with more information that goes. But with that, I'm going to hand over to Malcolm Howe of Cundall and allow him to take you through the detail of the report. Malcolm, thank you.
So without further ado, I'm going to be talking to you about the study that we've done on the application and performance of liquid cooling. How did we get involved in this? Well, about a year ago, Isotope invited us to carry out a review of their precision immersion liquid cooling solution. We've done a number of these engineering reviews before, and they've always been interesting exercises to participate in. We've been able to bring our industry perspective to the vendors' products and and we generally learn a lot ourselves from the process. We've also known Isotope from when they were a small startup company. We were keen to see how their technology has progressed over the last few years. One thing that I should like to emphasize is that when we do these engineering reviews, these studies, we always do them on the basis that we remain completely impartial and objective. We are not the marketing division of Isotope, and they didn't have any control over what we put into the report. So I'm going to start by quickly describing the objectives of the report and highlighting some of the drivers towards the adoption of liquid cooling. I'm also aware that not everyone on the call may be a mechanical engineer, so I'm going to be describing the different types of liquid cooling technology that exist, and also highlighting some of some further points that I believe will help you get a better understanding of the subject. So what were the objectives of the study? Firstly, to introduce the topic of liquid cooling in data centers with a particular focus on Isotope's chassis level precision immersion cooling and their direct-to-chip solutions, but also to compare the energy performance of liquid cooling with various air cooling solutions. I mean, this is something that seemed like an interesting thing to do. We don't think anybody else has done it before. At least there's nobody that we were able to find, no other reference studies out there that we were able to refer to. So as we started to get into the whole topic of liquid cooling, it became clear that there are a lot of drivers now towards the adoption of this technology. I mean, the most obvious one is increasing CPU power and increasing rack power density. And the graph on the left here, the screen shows the evolution of processor heat density, and the upward trend that those curves are showing is pretty clear. We're also seeing the emergence of new power-hungry applications such as AI, HPC, graphical streaming, and I mean, where this is all leading, in some areas at least, we are starting to come up against the limitations of what air cooling can support. There are other factors as well. National governments are bringing in targets to achieve net zero carbon. I think we heard from the G7 meeting just earlier in the week that there was some targets agreed there. And these are being translated into municipality regulation, codes, and planning policy aimed at reducing energy consumption and carbon emissions across the board. Given that data centers account for about 1% of global energy consumption, this legislation is obviously going to have a significant impact on our industry. So one of the ways in which we are already seeing this is planning policy pushing urban heat networks. Now, Nordic countries are well ahead in this regard. We've done several major projects in the Nordics. One of our data centers projects in Denmark currently recovers 45 megawatts of waste heat, which is sufficient to heat 7,000 homes in the city of Odense. But it's also something that's coming down the road here in the UK. There's other projects that we're currently working on here where we're being asked to look at similar things by planners. One final point is that the higher power densities that can be achieved with liquid cooling mean that fewer racks are required to achieve a given capacity, which can translate into a smaller data hall and potentially a smaller data center. Next thing I wanted to talk about is the ASHRAE liquid cooling guidelines. Many of you will be familiar with the ASHRAE TC 9.9 thermal guidelines for data processing environments. Well, TC 9.9 has also produced a similar set of guidelines for liquid cooling. And these provide classification of the water supply temperatures for the facility water system that provides cooling to liquid cooled racks and equipment. If you take a look at classes W3 through to W5, you can see that these temperatures are generally warmer than what you'd encounter in air cooling systems. You know, you'd be chilled water for CRAs or whatever. Also, in many locations across North America and Europe, these water temperatures could be achieved without the need for chillers or evaporative cooling. So there's potential for big energy savings there. The plant just needs to be dry air coolers, and because there's a larger approach temperature between ambient air and the water, the coils themselves don't need to be so big. So you've got a simpler plant that is of a smaller footprint and therefore cheaper to buy. Getting back to the point I made earlier about waste heat recovery, it's also a lot easier to recover data center waste heat from water at above 46 degrees C than it is from air at a lower temperature. Types of liquid cooling. Yes, the next thing I wanted to talk about. There are two main groups, direct chip and immersive, and then there are several subgroups reflecting single or two-phase cooling processes. With the immersive cooling, there's tub or tank full immersive solutions, which can be either single or two-phase, or there's the chassis precision immersive, which is Isotope's solution. Then there's the direct to plate Coldplate technology, and you can have hybrid forms that can be a mix of both strategies, and we'll get into the detail of that. I think I would also like to clarify that there are some technologies, cooling technologies, that are sometimes described as liquid cooling, but which are not. So hack coils, in-row cooling, rear door cooling, in-rack cooling. Water is delivered to the rack or close to the rack, but the cooling to the electronic components is by air. So this is not liquid cooling. Cold plates. So with cold plate, liquid cooled heat, with cold plates, a liquid cooled heat exchanger is fixed directly to the processor, and that conveys heat away through conduction. So it's a good technology. It requires good contact between the plate and the chip to get the conduction effect, and that's got to take account of thermal movement in both components. Fluids can be single or two-phase, and they don't need to be a dielectric fluid, as the fluid doesn't actually come into contact with the electronic componentry, and unless of course you get a leak, then you've got bigger problems. Cold plates can provide very high cooling capacity to the specific item that they serve, which is usually the processor, but they won't cool any of the other electronic components on the motherboard, so additional air cooling is also needed. Cold plates are relatively easy to integrate into conventional racks, and it's feasible to adapt air-cooled motherboards to accept cold plates, so it's quite a flexible technology. With tank or tub immersive cooling, the entire server motherboard is fully immersed in a dielectric fluid, and the fluid is then pumped through a heat exchanger, which takes away the heat. So you get a good even cooling across the whole of the server. This approach can provide very high cooling capacities, especially where two-phase liquids are concerned. I think I read somewhere that Microsoft was experimenting with 300 kilowatt tanks, so it gives you an idea of the scale of what these devices can achieve. A feature of full immersive cooling is that the server has to be removed from the tank for access, and this can certainly complicate maintenance. I mean, the fluid itself is at relatively high temperature. You wouldn't want to put your hand in there. And if you've got two-phase liquids, then the tank needs to be very tightly sealed so that the fluid doesn't boil off. So that again complicates access. Another feature of full immersive is these tanks is that they don't generally follow the form factor of a conventional IT rack. So the data hall layout would need to be adapted to suit the incorporation of these tanks. Just one further point to note with them is that, and this is the same with all immersive cooling and be it semi-immersive or full immersive, there's still a requirement for some cooling to the data hall. Most of the heat is taken away by the fluid, but you've still got things like cable losses and radiant losses from pipework that you need to deal with. With Isotope's precision immersive cooling, the server is contained within a sealed chassis, and the base of the chassis acts as a reservoir for the dielectric fluid. The fluid is then drawn up by some small circulating pumps and passed through a heat exchanger before being sent back to the electronic components, and then the heat exchanger is cooled by the facility water system. The process uses single phase fluid, but the chassis, unlike with a full immersive, the chassis is only filled to the depth of a few centimeters, and the fluid cascades over the server. It's not fully immersed in it. So the amount of fluid that's required is very much less than with the larger tub configurations. A big advantage of this type of approach is that the server can be accessed without needing to be removed from the chassis. Another advantage is that the chassis can be slid out of a standard OPC rack in the same way that a conventional server can, and the racks themselves can be integrated into a conventional data hall layout, so you could easily have a mixture of liquid and air-cooled racks within the same space, and that could be quite easily accommodated within conventional hot aisle and cold aisle architecture. Again, with the full immersive, you still need to have some air cooling to deal with pipework losses and cable losses, but the immersive side of things will capture, I think, at least 95% of the heat from the electronic components. I mean, David may clarify that. It might even be slightly higher than that. When thinking about all of this liquid cooling, I think it's important to think about how power is used. An important feature of liquid cooling, which is sometimes overlooked, is the way that the power is consumed at rack level. PUE considers the energy that is delivered to the rack, but not how that energy is used. So it's a bit of a blunt instrument in that respect. To address this, the clever guys at the Green Grid have come up with a couple of other metrics, which are ITUE and TUE. I don't know if any of you have come across those before, but ITUE is the ratio of total energy delivered to the IT racks to the total energy delivered to the electronic components. Those two are not the same. So it's effectively a PUE for the rack itself. TUE is the total power usage effectiveness. So that's obtained by ITUE times PUE. The reason why this is important is that with an air-cooled rack, up to 10% of the power supplied to the rack is going to the server fans, whereas the dielectric pumps that circulate fluid within an Isotope precision immersion server only account for about 3% of the rack power. So there's a 7% saving there. If you applied that to, say, a 1 megawatt data hall, that amounts to an additional 70 kilowatts of power that is available to your electronic components that would otherwise be going to just moving air through your rack. Power density versus rack count. This is another point that I wanted to highlight. It's the impact that power density has on rack count and data hall footprint. I know Jared's going to talk about this at more length later on in the presentation. Load densification translates into fewer racks needed to achieve the same target capacity or a greater amount of capacity available from a given number of racks. So again, if we take our 1 megawatt data hall and we fill it full of 5 kilowatt racks, then we'd have a rack count of 200, and we'd need 150 square meters to accommodate them. If we increase those that power density to 60 kilowatts a rack, which is certainly well within the capabilities of the Isotope precision immersion cooling, then that reduces down to just 17 racks, and you'd only need 12 meters squared of space to accommodate them. So, having got all of that out of the way, let's move on to the comparison study. So to recap, main objectives was to compare the performance of air and liquid cooling based upon a series of real-world scenarios. We prepared a detailed energy model for each scenario using bin weather data, and we approached some friendly plant manufacturers to get actual equipment selections and equipment performance data, which we plugged into PUE, WUE, and TUE calculations, and then we compared the OPEX cost savings that we got, and also looked at the spatial requirements for each one of these different scenarios. We had a lot of fun coming up with these different scenarios. We created some fictitious company names, and we put a little sort of a narrative against each of our imaginary data center developers, and that's all in the report. We have a hyperscale operator based in 2 locations in the USA, a colo developer based in London, and an edge operator based in Singapore. And there on the left there, you can see one of our little energy model schematics that we created, and the pie chart, which is showing the split of energy usage that came out of one of our PUE calculations. So we did this quite as thoroughly as we could. I have to say that the results were quite astounding. It came out better than I thought it would. The improvements that we were seeing from the adoption of liquid cooling were very significant across the board. And I mean, the standout example was Singapore, where the ability to ditch a lot of energy intensive chillers and water intensive cooling towers due to the higher ambient conditions of that locality really gave liquid cooling the edge, and showed some impressive results. I mean, if we look at the results here, total cost of cooling per kilowatt of IT power reduced by between 23 to 83% through the adoption of liquid cooling. Our CO2 emissions dropped from between 6.6% and 39.5%. And then there was also some impressive savings in water, again, particularly in Singapore, where we were getting away from the reliance on open circuit cooling towers, which was the base solution we modeled. We're showing there a 96% saving in water. You'll have to read the full report, which you can be getting from David. Before I hand over to Jared, I thought I'd just leave you some final thoughts. I believe liquid cooling is a technology that's moment has arrived. I think it can provide some very high capacity cooling, and the cooling is provided where it's needed, where the hotspots are. Facility water systems can be operated without the need of expensive and energy consuming chiller plant, and even in a lot of locations you don't need evaporative cooling, so you're saving on the water. Utilization of rack power is much better when you consider the difference in ITUE because of the saving on the server fans. It's easy to integrate with waste heat recovery systems, which is going to assist when planning and environmental targets come along. And the plant is relatively cheap and simple, and the rack count and the density allows for fewer racks in your data center or smaller data centers to achieve the same capacity in your technical space. So I think it's got a lot going for it. So I'm now going to hand over to Jared.
Thank you very much, Malcolm. Very interesting and some really useful points raised. I mean, one of the highlights just before I talk about my angle on this is the 70 kilowatts worth of reduction in power consumed by the server as a whole because of taking the fans out. I mean, that's a direct sort of feed into reducing your UPS sizing by 70 kilowatts per megawatt, which plays into additional energy wastage and savings, but also savings in capex. So I think really exciting. I'm from KO Data, and just for those of you who don't know about KO Data, we were launched in 2014 on a campus in Harlow, primarily targeting some of the business that we expect to find on the London to Stansted Innovation Corridor and up to Cambridge, looking at life sciences. We've got a campus there pre-planned for 4 data centres, each with nominally sort of 9 or 10 megawatts each, across a 15-acre campus. One of the things that we focused on is keeping ahead of design trends and using best practice. So we do sit on the Open Compute Foundation board, not on the board, sorry, on the committees for data centre facilities. And because of that, we registered and became one of the first data centres to be open compute ready. One of the things that we are seeing, and part of the life science approach that we've taken, is the use of much higher density computing. We've recently installed an NVIDIA supercomputer called Cambridge One, which is helping with COVID research and many other sort of biomedical aspects. And one thing we are absolutely committed to is sustainability. So we do use renewable energy. We've just taken the step of removing all fossil fuels from our backup power systems by using hydro-treated vegetable oil, BREEAM Excellent, and we operate an ultra-low PUE for air systems. And that leads me on really to where we are, the comparison between air systems and water, and hoping to drive down that overall PUE. So if I could move on to the next slide. What is high performance computing? Well, what you've got there is a little photo of an NVIDIA DGX SuperPod. It's very similar to the architecture that we've had installed at our facility in Harlow. And what we're seeing is that although this is all air cooled, it's driving densities up sort of 20 kilowatts a rack easily, and beyond that, up towards the 50 kilowatts potentially. That gives us some sort of real problems to think about in a data center. Particularly one that's using low energy systems where it's involved with air-to-air heat exchangers, because it determines the physics or the geometry of your data center. You've got to get the air in and out on an outside wall, and that therefore drives longer and longer data halls to get more and more cooling to serve the higher and higher density loads. But the interesting thing is, the amount of racks that you can put in that longer and longer hall is getting smaller and smaller. So you end up with a sort of catch-22 circle of wasting space, basically. And wasting space is wasting materials, is not being very sustainable. So I think it's very exciting for us to be involved with the advent of different types of liquid cooling. And we've seen quite a few of those, and we've got some really exciting things going on, particularly around Isotope and their products. So if we could move on to the next slide. Our colocation, how is colocation trying to adapt to liquid cooling and HPC computing? As I mentioned, we are open compute ready. I actually sit on the data center facility committee that meets monthly, and there's a subcommittee of that which is on advanced cooling systems, and that's really not to drive liquid cooling, but it's to observe the trends in liquid cooling, pick up on that and make sure that best practices are being adopted for how data centers are engineered to support that liquid cooling, because it clearly is the way forward. So we've come up with a data center, and that's really sort of gathered from my own experience and others within the management team at KO, from dealing with literally hundreds of data centers around the globe. We've gone for column-free environments, so it gives much more flexibility on how you lay the equipment out. 15 kilonewton floors. A lot of these racks with liquid cooling are getting heavier, pre-populated, so we need the ability to roll these in straight into the data center and get return from the racks. One thing we are doing, obviously, as I mentioned, to drive sustainability is to use 100% renewable energy. We have our own on-site substation fed from the grid, and we offer 100% uptime on our systems. Now, that's not to say statistically you could prove they're probably less than 100%, but because of the simplicity and the straightforward nature, we're confident that we can support that sort of 100% performance. At the moment, we're using a basis of design that uses non-refrigerant based free air cooling. Now, we do achieve a very respectable 1.2 PUE on that, and we can operate within the recommended or allowable all year round. What it means, though, is that whilst 6 months of the year we're dry, there are 6 months of the year when, to varying extents, we do use water. And to Malcolm's point, using sort of closed systems with liquid cooling helps reduce that water draw quite considerably. We obviously look at doing bespoke deployments, so we can accommodate sort of hybrid systems. So we use a blend of our air-cooled systems, and then also can populate the same space with certain of the liquid-cooled installations. I think if we move on to the next slide, we are seeing densities definitely starting to shoot up. Although I've been in the industry for over 20 years and people have been talking about increasing densities, it has taken quite a while for this to materialize, but we really are seeing that. As the uptime information there sort of indicates, 12 racks as a sort of average is becoming quite a reality. We quite regularly let space on a basis of 10 kilowatts per rack average, but even within those customers, we are finding that some of them have moved to dual 32 amp three-phase sockets, so potentially up to 44 kilowatts per rack. And we're actually now planning some of those installations as we speak. As Malcolm says, there are limitations with air. And one of the big things is obviously the 4-to-1 ratio of heat transfer, which ultimately determines the sort of size that you can sort of accommodate racks in. What we're finding is that as we go up beyond the sort of 20 kilowatts per rack limit, the velocities of air, if you try and overpack a data center with racks, become too great in certain areas, create negative pressures between hot and cold aisles, and actually drag air back, however well you seal the hot aisle containment, back into the aisle and re-entrain it into the servers. So something really needs to be done. One of the ways of combating that is to space the equipment out. But as Malcolm was saying, if you go from 200 racks to do a certain amount of kilowatts down to 17, you end up with an awful lot of real estate that someone's paid for that it's very difficult to get the investment back on. If we move on to the next slide, clearly high density is driving this cooling sort of change. So we're doing some very exciting work with Isotope. We've done some very interesting ethereal work as well. So listening to what goes on in the ACF meetings at Open Compute is very interesting. We've been to a lot of discussions, a lot of exhibitions where certain offerings are on the market. We've done some planning around Coldplate solutions. But what I think's very exciting about the Isotope deployment is that really within the same data center as our normal air-cooled delivered data center, we can accommodate the racks just in the same way as we would do any other rack. They use very standard racks. Obviously, we need to take a water supply to those. But in terms of planning the space, it becomes so much more easy to do it with that type of installation. Clearly, the use of dry coolers means that we're using far less energy to drive the actual cooling process than you would with chillers. And we've actually got a live demonstration test lab that's going on where we have around about just about 120, 130 kilowatts worth of capacity across 5 racks, and they're sitting there very, very low partial mechanical PUE, and really drives that overall efficiency. Clearly within our system we've still got the electrical PUE to think about, but as Malcolm says, with the 7% reduction in the take from fan power, that can only improve the losses that you get from the electrical system anyway. So I think, very exciting to be involved. Would love the opportunity to take more questions from anybody as we go into the Q&A. But I think, it's certainly something that's very, very here and now. And, it'll be very soon when we're actually starting to deploy larger scale deployments. All right, just to sort of wrap up, in terms of the advantages of liquid cooling, I think clearly maximizing that available power supply usage. So 7% less for the individual kilowatts of IT that you're using means that you've got 7% more IT that you can power. Clearly reducing the densities. I think if you go from the top left-hand corner down to the bottom right-hand corner, you can see the sort of shrinkage that we're talking about. So in the space of a quarter of the data center, you can still generate the same sort of income from the full data center at the same sort of kilowatt pricing, but you're spending less in capex. Reduced PUEs, so absolutely critical, not only to reducing total cost of ownership for customers, but also reducing greenhouse gas emissions, CO2. As we touched on, in our own particular data center, standard air-cooled technology, our suites can normally accommodate, they're designed to accommodate 2.2 megawatts across 9,000 square feet, 850 square meters. And that's based on 440 racks at 5 kilowatts. As we've seen with the precision liquid cooling, we're going to increase the density or conversely decrease the size. So we could be doing somewhere in the region of 8 to 10 megawatts in a complete hall, subject to getting the power at the site. And we really are seeing people using air systems trying to drive that, but encountering difficulties. So I think really, if you want the reliability and the performance, going liquid cooled and direct to chip is one of the best ways of doing it. And I think that takes me to the end. And with that, I'd like to hand back to Sophia and address some of the questions that might have been coming in. Thank you.
Thanks, Gerard. Thanks, everyone. Really interesting presentations. I do see there's a few questions coming in the chat box, but perhaps to get us started, Gerard, I'd like to know a bit more about your operator experience of liquid cooling. So I think you mentioned that there is already an installation that's live in your facility. Maybe you could expand a bit more on that, but I'm also keen to know in what kind of timescale are you expecting to see the liquid cooling side of things grow and the air side diminish, and maybe have a bit of a feel for what's the customer demand like? Where do you think it's going and how quickly?
Yeah, it would be nice to put an exact finger on it, and if I had a crystal ball, we could get there. But I mean, it is something that is definitely coming. So we have a live operation on site at the moment. It fits in exactly the same sort of standard space that we would use in our standard hall. Solid concrete floor, absolutely perfect for it. Gives it the ability to bolt down because obviously the racks are heavier, so you need that stability. We have the external cooling space that we can use with either indirect dry coolers, indirect air coolers, which are wet during the summer months, or we can put dry coolers on that space as well. So very adaptable, and means that we can swap between the two or have hybrid installations. In terms of real timing, it's very difficult to put an actual figure on, you know, when are we going to do the first complete data hall. I think we're probably never going to do a complete data hall of liquid cooling, because there's always going to be equipment that's probably going to stay, like legacy equipment in data centers now, is going to stay air cooled. You know, maybe it's not worth the investment to actually water cool that. So, but I think what we will see is 90 and upward % move towards liquid cooling in time. But I think there's still going to be a certain amount of air cooling in a room. One of the proposals I was talking about was for a large predictive model computer. That was actually based around Coldplate, but that was, again, 10 megawatts worth of capacity in roughly about 800 meters squared. Huge densification. But the trials we're running with Isotope show that that's eminently doable in very small spaces. It gives you the ability to drive up that energy efficiency, and as an operator, actually create more usable space on the campus compared to doing it with air. So I guess if you want an actual time, I've been a bit of a politician there. Certainly, I think we're going to see the next 12, 24 months, significant scale of deployments. But I guess, you know, before we're actually doing that on a regular basis, it's probably going to be the 3 years and beyond model, I would think. But I'd be interested to hear other people's views on that.
Okay, great. Thanks for that. I'm just picking up on some of the other questions that have been coming in. So I guess a question to any of the panelists. What are the differences moving from an air-cooled model to a liquid-cooled model from an operational perspective? And what are some of the barriers maybe where people might be reluctant to make such a wholesale change in the way that they do things? We've heard a lot about the benefits, but obviously there's challenges which go with change. So I'm just interested to hear people's perspective on how.
I'm sure Malcolm will have a view on it. But if I could jump in from an operational point of view.
Go ahead, Jared.
Yeah, from an operational point of view, you know, I think managing a system with water as the prime sort of cooling medium during the summer months does create certain amounts of I won't say problems, but a certain amount of management. You know, there's water treatment, reverse osmosis for some equipment that we use, but a lot of filtration, some wastewater, and so that does create an additional sort of workload on the operation side. Going with sealed systems, dry air coolers, clearly gives us the opportunity to make life a little bit simpler on site. It's certainly more dense in terms of the way we pack our equipment out in the sort of heat rejection yard. So overall, I'd say it makes the data center operation easier to deal with. But I'm sure Malcolm will have a view, certainly on the technical side of things.
Yeah, I mean, I was thinking of the barriers that some operators might have when considering liquid cooling and the implications of that. And I mean, one obvious one is bringing water into their data hall. Some people are just not at all keen on that. There are ways of addressing it. I mean, the water can run at low level beneath the racks. The other thing to bear in mind is that the facility water loop that's coming up to the server itself, that's coming off of a cooling distribution unit, and it's at relatively low pressure. So if you do get a problem, it's not spraying water across equipment that doesn't respond well to getting wet. But you know, there is a concern there that would need to be overcome with double containment pipe and leak detection, and we've even seen sub-atmospheric pumping systems that can be applied to liquid-cooled installations, where if you get a leak in the pipework, you get air leaking into the pipe rather than water leaking out of it. And we have looked into those. I mean, it's quite a good, neat technology, and it does work, but it only works on relatively small installations. If you've got a very large data hall, the pressures that you need to pump the water, just to circulate the water around the hall, can be such that you know, you end up with very low pressures at the pump, which is not, you get cavitation issues. But yeah, I mean, bringing water into the hall, I think, is one area that would certainly be a concern to some operators.
Although, if I could just jump back in there, you know, in actual fact, until recently, when we went for indirect air and maybe even direct, some people, most data centers had lots of water in there.
Well, exactly.
Yeah, chilled water circuit or a condenser water circuit. So
yeah,
it's really about using the appropriate management system to manage that water containment, isn't it? So
yeah,
I think, yeah, as long as you have something that's proven and reliable, then it's really no different than data centers have been for the last 20 years.
mm-hmm. Yeah.
Malcolm, can I ask you another question, which is design related? So
mm-hmm.
how do you accommodate this requirement where we know that we're going to be going through a transition? So most of our design up to now is looking at air cooling. We know that we need to accommodate liquid cooling in the future. As a designer, not knowing exactly when we're going to make this pivot, how do you deal with that? How do you keep it flexible and open to the two options?
Well, one of the, I mean, in actual fact, one of the scenarios that we modeled was an imaginary colo operator in London who had an indirect air cooled data center in a multi-story building. And as he'd been fitting out his building, he'd come to the last data hall, and none of the previous halls had reached their design level. So he had a whole load of spare power available in the building. So the scenario we modeled was to put in a supplementary cooling system with heat exchangers to a cooling loop, where you could have a mixture of air-cooled racks supplemented by liquid-cooled racks. So the air cooling would basically remain as it was with the indirect air, and the top-up cooling would be provided for the liquid-cooled racks. And I could see that some data center operator, and we've already been speaking to some people who sort of want to, you know, they don't know that they've got a definite requirement for it, but they want to future-proof their data centers against the possibility of a customer turning up and saying, I'd like to put in some HPC or some liquid cooled racks. Can you accommodate that? So we're putting in or planning in the space for the infrastructure that could support that. So risers, heat exchangers, space for dry air coolers up on the roof as a supplementary system. And you know, the scenario that we looked at in the report, we took a 1.6 megawatt hall up to 2.4 megawatts by just converting some of the racks to liquid cooled and focusing the IACs on a smaller number of air cooled racks at a slightly elevated capacity, and then filling up the back of the data hall with liquid cooled racks at a much higher capacity. So I can imagine that, well, you know, we tried to make that a real world scenario, and it does reflect conversations that we've had with people.
Okay. David, do you have anything to add on maybe what things customers need to think about when they're looking into the feasibility of moving towards liquid cooling?
David, you've got my problem.
I think the first thing I would say is, you know, huge thanks to Malcolm and Gerard for the contributions, and also very wise and sage responses to this. You know, this is not as simple as some would try and suggest it is. You know, there have been magic wand type approaches. Don't worry about it, you can just go liquid cooling and it's that easy. It isn't. And the approaches that people have taken here, there really are benefits. It will be a hybrid world for some considerable time. We will have to coexist between air and liquid. So, what we've seen is, from everybody from like really exciting hyperscale projects to tier 1 OEMs and others, is that we're seeing very, very practical, well thought through implementations. People are taking care to think about not just the infrastructure, but the operations, the service, the maintenance, the scale of what you do. And I think I'm really impressed at the amount of thinking that's going on in the industry and the real solid preparation for it. So as people prepare for this, I think absolutely right. There's nothing that needs to be scary about the data hall. But it is about getting good quality design. It is about actually starting to explore for it. Liquid cooling is definitely coming. Any data hall that thinks that they don't need to worry about it for the next few years is probably going to be in trouble. So I think, the timing, I would concur, I think, with Gerard on that is pretty appropriate. A lot of scale and then moving. So, thinking about those service maintenance approaches being easier, thinking about how to model your OPEX and CAPEX being cheaper, and then how to make that transition. There's a lot of people kind of waiting in the wings. And I think that's the timely importance of this particular report, is we wanted to make something available that took us beyond theory into practice and really started to give people really solid questions and answers there. So I guess the short answer, having waffled there, would be come and get a copy and read the report. And I think it will be highly illuminating.
Great, thank you. Another question kind of open to anyone. So I think quite often a theme in data centers has been this interface between the worlds of IT and the worlds of facilities. And quite often, they're different parts of the organizational tree. How closely do they work together? I kind of see this technology as forcing the two elements to work more closely together, because the interface of cooling and IT equipment is getting physically closer. I was wondering if anyone had any kind of reflections on how that might play out.
If I may go first, I'd like to comment on that. I think it's an absolutely brilliant question. And when we think about the challenges that we face, both in the ability to remove cooling and power and such like as constraints. Today, there are constraints on our ability to deploy enough IT, to get enough software running, to run AI, etc. So the first thing we want to do is get out of being in a constrained mode to one where we can really allow people to fly. And we've got really significant environmental challenges. Simply being efficient will not be the answer. The kind of stuff that's coming in scope 1, scope 2, scope 3, challenges that are going to be on businesses, to really go net zero and beyond. This stuff's going to come under a lot of interaction and interest. So the model of we've got one thing over here and one thing over here, and neither the twain shall meet is bust. When we start to think about TCO, total cost of ownership, that's going to be total environmental cost of ownership. What's the entire carbon footprint of this entire supply chain, etc. So the idea that we can look at things in isolation is absolute nonsense. And that was one of the things we really set out at Isotope to do, was to say, how do you take the Venn diagram and kind of draw the circle it takes, the best of all of these worlds together, and creates that kind of stepping stone between them and creates a roadmap through. So the days when they're separate are over. To some extent, increasingly what we're doing is bringing infrastructure to the device, and that simplifies, reduces costs, and it also makes it ubiquitous. Our technology works the same in the middle of a farm field as it does in a data center. So when somebody invests in the IT and in the IP, they're able to actually deploy it wherever they will. And that's a really powerful thing. We start to really enable IT to live wherever it wants to, rather than kind of hotels that it's stranded in, if you like. So that conjoining of IT and infrastructure together can only be good for us. So we would say definitely the joining up of it, and that TCO modeling will be informative to businesses and will drive better designs, better behavior, and better financial operations as a result. Malcolm, Gerard, any thoughts?
Mm-hmm. Yeah, I mean, I'll pitch in very quickly. I realise we've not got much time, but you know, when we got low density environments, actually, it's been very easy for colo operators to be, if you like, lazy and just let people get on with putting servers as and where they want to. We've seen the tightening of that with the introduction of hot aisle containment to actually contain and stop the air mixing. But if I go back to the sort of late 90s, air was just bobbing around in the data center, mixing, very inefficient. But as we, as you say, bring the infrastructure closer into the IT, you're getting back to a situation where you're almost creating an IBM mainframe. You know, it becomes one being, if you like, and you've got to work between facilities and the IT to make sure that you get that right coordination. I'll hand over to Malcolm on that, because I know we've got very little time.
Yeah, just the only thought that I'd have on that one. I mean, there's some practical issues to do with commissioning. You know, when you have an air-cooled data center, we're all used to putting emulators in there and blowing lots of hot air around and testing our systems. With a liquid-cooled facility, it's a little bit more complicated. You've got to have effectively an emulator that can sit in a liquid-cooled environment to drive that process, or at least a means of circulating water around the circuit and proving flows and whatever, without necessarily the IT kit being there when you're commissioning the system. So there's a few things like that you've got to overcome, but yeah, it's certainly a merging of IT and engineering. Yeah.
Okay, thanks for that. I'm conscious that there's many questions kind of coming through
Yeah.
in the boxes. Some of them I know are quite specific, and I believe the answers to a lot of them are available in your study. So I guess that's a recommendation to download and read it.
If I may, Sophia,
Sure.
there is one. Somebody's asked the question, you know, that I'd like to cover, because you know, does this just apply to the servers or to the whole stack? Our technology applies to the whole stack. The implementation that we have in KO has got everything from spinning disks to power supplies to it's the whole shebang. Has been liquid cooled, in rack, serviceable, hot swappable, you name it. So just to put that one in there, yes, and we'd love to share more with that. But there's a lot of great questions. I think let's make sure we'll get back to everybody with answers for all their questions, and so grateful for them. That's there. Anyway, Sophia.
Okay, I think our time is up. So I'd just like to close by thanking all of the panelists for their insights. Thank you for joining. Thanks for all of the great questions. And yeah, look forward to more conversations about liquid cooling.
Thank you very much indeed. Cheers.
Thanks, everybody. Thanks for joining.
Bye.
Bye-bye.